Good morning, everyone. I'm Riko Tutko from Electrical Engineering Department of ITS Surabaya, Indonesia. First of all, thank you for the opportunity to present at the International Conference on Technology and Policy in Energy and Electric Power 2022. The title of our presentation is Optimal Scheduling of Battery Flywheel Hybrid Energy Storage System for Off-Grid Power System with Renewable Energy. Introduction. The issue of climate change is a crucial reason for the expansion of renewable energy sources. The national energy policy of the Indonesian government aims to share renewable energy to at least 23% in 2025 and 31% in 2050. The energy storage technology can help overcome issues such as renewable energy variability and distribution power variability. A hybrid energy storage system comprises two or more storages with complementary electrical charging or discharging characteristics to meet energy and load power demands. The combination of energy storage expects to provide high efficiency, high power and energy density, longer life, and lower generation costs. The paper proposed to design optimal scheduling of hybrid energy storage in a system powered by renewable energy source. The advantages of each type of energy storage technology are considered in has to work on optimal power sharing. Research gap. Using nonlinear optimization programming methods, the approach in this method will be to schedule power sharing for each energy storage based on minimizing the total project cost, operation and maintenance cost, and the life cycle of each type of energy storage technology. The optimal power sharing of the two internal energy storage technologies is has achieved by considering the RAM rates of the battery energy storage and flywheel energy storage. The system considered in our study consists of a solar power system, a wind power system, battery energy storage, flywheel energy storage, and the inverter that connect each part to the AC or DC bus, as shown in figure 1, and then enter the inverter before being distributed to the load. There is tabel prediction for cost and parameter of battery and flywheel energy storage. The batteries that will be used are lithium-ion, and the flywheel is conventional model. The predicted price year to be used in from 2018 to 2025. In this section is the calculation of capital recovery factor, or CRF, is the total annual cost recovery factor of each type of energy storage technology is influenced by the lifetime of the energy storage type. The total project cost is determined by amount of capital cost, power conversion system cost, balance of plant cost, construction and commissioning cost, and then the total cost will be normalized per hour. And also the operation and maintenance cost will be normalized per hour. The objective function, TPCN or total project cost normalized per hour plus ONMCN or operation and maintenance cost normalized per hour, and the following result here, the following X1 to X24 for indexing battery and X25 to X48 for indexing flywheel. This is the mathematical formulation for nonlinear programming. There is an objective function, equality constraint, and inequality constraints. The flowchart starts with inputting the data, putting the objective function, variable control solution, and constraint, and using F-min-con optimization to calculate optimal scheduling of hash. The result is visible and satisfied will be stopped, and if not yet, will be restructured to calculate more. There is 24-hour load demand shown in figure 4. The load will be assumed to be supplied by a renewable energy generator combined with hybrid energy storage system. Figure 5 shows that hourly wind energy value varies. Solar power increases every hour as it approaches noon and reaches its peak at the 13th hour, and after it decreases. This is closely related to solar radiation as an energy source. The total power from the combination of solar power and wind power will supply the load, and the rest will go to energy storage. In the figure 6 shows that P-hash is the difference between the power generated by renewable energy sources and the load demand. The graph shows the energy hash hourly, but the optimal scheduling for base and fast is not yet known. Base and fast at T0, the state of charge is 60% of the capacity. The energy capacity of base and fast is 800 kilowatt hours and 300 kilowatt hour respectively. Figure 7 shows an hourly power graph at base that does not consider the ramp rate. It is known that power fluctuations are quite high, reaching almost 100 kilowatt, which is understandable because there is no ramp rate to limit and maximize the supply for hash to the load only by considering the total project cost and operation and maintenance cost, which storage technology is less expensive. It is so that fast work with quite weak power because fast is higher total project cost. In figure 8, performance result of base after giving a lower RAM rate, 75 kilowatt per hour to 20 kilowatt per hour. It is clear in figure 8. Now the power fluctuation will decrease and the battery power performance will be smoother, which previously peaked at 90 kilowatt in the 23rd hour to 54 kilowatt. Next, when comparing fast power in graph figure 7 and figure 8, it is known that fast power performance increases because when the RAM rate of base is reduced, the power responsibility is transferred to the fast. This condition becomes a realistic condition because the fast provides high power but has the disadvantage of low energy density. The last conclusion, the optimal of hash scheduling without considering RAM rate, the optimization will work to adjust the lower price for each type of energy storage technology. Simulation result for optimal hash scheduling when the RAM rate is considered on the base, the power performance becomes smoother on the base, as shown by the difference between figure 7 and smoother in the figure 8 at the same time. Fast power performance increases because when the RAM rate of base is reduced, the power responsibility is transferred to the fast. Then fast has a weak energy density. It will combine with base, which has a high energy density. Base will work at the low peak power with low RAM rate and extend the life cycle of base. Optimal hash scheduling overcomes the weakness of base because high power density are compensated by fast, and the weakness of fast as low energy density can be helped by base. And finally, thank you for your attention. Does any have any question or comment about the presentation? Please.